Bueno, bienvenidos a todos de nuevo. Pues es un placer presentar a Raúl Álvarez del Instituto de Matemáticas de la UNAM en su sede Cuernavaca, que nos va a hablar de una clasificación homotópica de estructuras spin 7 con aplicaciones a la holonomía riemanniana especial.
Muchas gracias. Bueno, la plática va a ser en inglés. Solamente quiero decir unas palabras en español. Primero, una disculpa. Casi todos hablamos español, pero quiero hacer esta plática para razones de promoción, como decía, sin pena. Y bueno, so I'm switching to English now. And you can check details about this work in this archive. And actually, today I want to talk about this theorem. And this theorem is, it is not the same version that appears in this reference. This is kind of like an absolute version. And in the preprint, you can find a relative version where I consider not only compact manifolds, but, sorry, here is closed. So today I'm going to consider closed manifolds with these properties. And in the archive, you can find the version when the manifold has boundary, and it's a little bit more interesting. But in any case, I'm going to talk about a classification of spin 7 structures that I found recently, early in this year. And so this theorem, actually, the proof of this theorem is not very interesting, as you will see. What I find interesting, though, is the fact, kind of like the setup on which this theorem belongs. So since there are analysts in the audience, I want to convince you that this theorem actually counts components in a function space. So let me begin with a brief introduction to spin geometry. I think on Thursday on Gerardo's talk we learned a little bit about spin geometry. So I'm going to add a little things to this idea. So spin geometry is basically, it relies on the existence of this isomorphism between the fundamental group of the special orthogonal group and the integers mod 2 for n bigger or equal to 3. And this isomorphism is actually induced by a diffeomorphism that exists precisely in dimension 3 between the special orthogonal group in 3 dimensions and the real projective space. So one consequence of this isomorphism is that there is a simply connected group, which we usually call the spin group, that covers the group SON in a 2-to-1 fashion, right? So this is very well known, and from this you can see that every representation of SON pulls back to the universal cover. So the main point in spin geometry is that there are representations of spin n that do not descend to SON. Actually, in Gerardo's talk, we saw a way to explicitly define this group as a subspace of the Clifford algebra, and the so-called spin representation, which is going to be like a fundamental object of this talk, can be constructed out of representations of Clifford algebra. So let me just discuss this for any n, and I will give examples in dimension 7 and 8. So the spin representation, is a representation into a bigger space. Well, in some cases, it's much bigger than the dimension. This n is much bigger than n, than small n, sorry. And so this representation does not descend to SON. So, for example, I can consider, well, just ignore this title for a bit. Because in dimension 7, the 7-dimensional representation is eight-dimensional. So, sorry, 7. It lands on SO8. And in dimension 8, this representation is 16-dimensional, but it splits. SO16. And the key point here is that this 8-dimensional representation splits as a sum of two representations of dimension 8. So these are the so-called positive and negative spin representations. And as I mentioned, they are 8-dimensional, right? So of course you can say a lot about these things, but to give you a property that is going to be important for us later, I will say that this representation is faithful, meaning that this homomorphism is injective, and this will be important soon. But now, why I'm interested in these representations? Well, precisely because of the title that I was telling you to ignore. In Berger classification that we all know, and if not, we should, or how was the? I mean, this is one of the this is one of the key results in differential geometry. Berger classified all the possible representation that can appear as holonomy representations of Riemannian manifolds, of non-symmetric and irreducible Riemannian manifolds. And there are two exceptional cases in that classification. One of them is precisely given by the spin 7 representation, this one that I have here. So that's kind of like the motivation to study this type of this structure, right? Because it's one of the exceptional examples in Berger's classification. So I'm going to use this Blackboard just. I will erase this soon, but just to point out one consequence of the fact that if I have a Riemannian metric with holonomy in a spin 7, then there are some nice consequences that follow. And the first one, the obvious one, is that if my Riemannian manifold has a metric with holonomy contained inside spin 7, by this I mean contained in the image of this embedding, but of course it's just the same as the group. And then the structure group of the tangent bundle reduces to spin 7, right? You will see in a minute what does this means in more concrete terms, but this is kind of like the obvious consequence of having holonomy in spin 7. So let me see. So in order to understand more concretely what does this mean, let me just discuss this diagram that is kind of like the main diagram in today's talk. So here I have in the bottom row of this diagram, I have the spin 7 representation, and as I already told you, it lands on SO8, and we know that SO8 is covered by spin 8, and since this group is simply connected by definition, I can lift this embedding to the universal cover. And actually, I can, well, we can pick a specific lifting, satisfying that the image of such a lifting coincides precisely with the stabilizer of a unit spinor. By the way, I forgot to mention, but the elements in the representation space of the spin groups are called spinors. So, okay, so the main content of this blackboard is that the image of this map of this lifting fixes a spinor, right? Which I can choose to have norm 1. So if I, how do you say in English this? If you take a close look and to that blackboard and this blackboard, you can deduce that one consequence of having holonomy inside spin 7 is that the manifold should be spin. And this is one consequence of this. And moreover, the positive spinor bundle, which is, since my manifold I now know that is spin, there is a spin structure, which I'll denote by P. And the positive spinor bundle is an associated bundle to that spin structure and to this positive spinor representation. And this bundle, which is associated to this data, splits, right? I split a line of this bundle, a trivial line, precisely because the image of this map is the stabilizer. Does that make sense for everyone? Okay, so this is kind of like the main consequence, and this happens, of course, if and only if the Euler class of the positive spinor bundle vanishes, right? So now I can give a more concrete condition, that a necessary condition for the existence of spin 7 metrics. So it is a theorem by Gray and Green from the 70s. And they computed the Euler class of the positive spinor bundle. And the result is that 16 times this Euler class is precisely equal to, let me see, 4 times the second Pontryagin class minus the first Pontryagin class squared plus 8 times the usual Euler class of the manifold, right? So from this, we get non-examples. For example, non-examples. If I take W as the H sphere, then we know that the first Pontryagin class and the second Pontryagin classes are 0, and the Euler class is 2. So in this case, the positive spinor bundle of the H sphere is actually 16, which is not 0, as far as I know. So the conclusion here is that this sphere cannot admit a metric with holonomy contained in spin 7, right? So if instead I consider, well, and that's it, that's a non-example, right? So I want to be optimistic, and so I want to give an example, a positive example, and instead I will take the quaternionic projective plane, which is a manifold, and this thing has, let me see, first Pontryagin class equal to 2, the second Pontryagin class is 7, and the Euler class is -3. So if you compute, if you plug this data in this formula, what you get is 0, right? Because HP2 bar, here I have 4 times 2 minus, no, sorry, 4 times 7 minus 2 squared plus 8 times -3, which is minus 24. And from here, I have 28 minus 4 minus 24, and this is actually 0, right? So this, of course, is only a necessary condition, right? So an open question, I mean, if you want to become famous, you can try to to prove that this manifold has spin 7 holonomy metric. It's an open question. And now I want to discuss a bit under which conditions, or what is the thing that we need to know in order to tackle such questions, right? So it's, oh, sorry. Okay, let's use this. No, this is important. Probably. Okay, so spin 7 geometry in a nutshell. Okay. Spin 7 geometry. So first, a definition, which is important. A geometric spin 7 structure is a positive spinor field, right? It is a section of the unit bundle associated to the positive spinor bundle. And that's my definition for a geometric. And here, notice that I'm using the word geometric, and in theorem it just says spin structure. So there will be a difference that you will see in a minute. But if you have a geometric spin structure, then you have for free a self-dual 4-form. And given by this expression. Where these pointy brackets refer to the metric in the positive spinor bundle. And we know that since spin 7 is contained in SO8, this bundle has a metric, is this one, and also an orientation. And also we know that the spinors are a module over the Clifford algebra. So in particular, you can multiply vectors by spinors and get back spinors. So what you do is you take this polynomial, this order 4 polynomial in your vector fields B, Z, Y, and X, and you do this, and then you can check that this thing is a 4-form that is self-dual, and actually it's positive, meaning that its squares is positive. And also, using this form, you can define a metric. And here's the connection between this topological story and the geometric picture. The second thing you can associate to this data, to this geometric spin 7 structure, is a metric that you get from solving this very complicated equation. So what do I have here? Well, this notation means that I fix a vector field, let's say Y, and I put it in the first entry of this form. So this becomes a 3-form. If I do the same with X, this whole thing is a 2-form. So if I square it, I get a 4-form. And then I multiply that 4-form by this 4-form. I get an 8-form in a 8-dimensional manifold, orientable manifold, actually. So it should be a multiple of the volume form of the metric. So the multiple that appears in this equation is precisely a metric. It's a number that depends bilinearly and non-degenerate in the metric. And this relation is highly nonlinear, right? So in order to find the coefficients of the metric in terms of the coefficients of the form, which depend, of course, on the coefficients of the spinor, you have to do crazy things, right? Solve this. But in any case, now I can state a theorem due to Marisa Fernandez from 86, which says that the holonomy of my manifold with this specific metric is contained inside spin 7 if and only if my form is closed, right? So here's, for the analyst, here's a interesting problem that you can study. Don't be fooled. This equation is not linear, precisely because phi is self-dual, right? So here in the Hodge star depends on the metric, and so this equation is highly nonlinear. But in any case, this gives a nice criterion to decide whether a Riemannian manifold has a metric with holonomy spin 7. And of course, this happens. This last condition happens if and only if the spinor is parallel, which you can just, it follows from a simple computation using this identity. But then a corollary, which was known to Bonan in 66, and then also to Hitchin in 74, I guess, and to Friedrich. I hope I'm not making any mistake in this name, but 80 something, 80 what? 82. It says that this manifold should be Ricci flat, right? Because it has a parallel spinor, so the Ricci of this G5 is 0. So let me change chalk. The time, okay. So one last comment about necessary conditions for the existence of spin 7 holonomy metric is a theorem of Joyce. Well, ignore again well, you don't have to ignore it. A theorem of Joyce, very restrictive from 96, is that, right? If the holonomy of any metric is contained, not this G5, any metric, if the holonomy is contained inside the spin 7, then the fundamental group of this manifold should be trivial. This is a very restrictive condition, but again, it's only necessary. It is not sufficient. Actually, no one knows necessary and sufficient conditions for the existence of such metrics. But in any case, the manifolds that I am interested in are simply connected. And that explains why, well, this is not the complete explanation, but that justifies this assumption on the fundamental group. You will see in a minute why you need to impose such condition. And actually, you cannot, to my knowledge, you cannot do better. But in any case, do you have any questions so far? Because I'm going to give a sketch of the proof of this result now. Anyone? Please? Sorry? Yeah, there are two types, I guess. On this topological consequence, assuming that no, as far as I know, there are not. No, but it would be very nice to. It's something to to consider. But as far as I know, there are no results like this. If you, instead of asking full holonomy, you just stay in other classes of spin 7 metrics. Okay, so any other question? No? Okay, so now the proof. And now, I'm sorry, but I'm going to reveal myself. I'm not a geometer. Oh, well. I'm just a topologist, you know. So what can I do? Well, I do topology. Oh, the proof. Yes, and actually, it is, I don't know, it's what it is, but the thing is that the proof you're going to see uses machinery from the 40s, the steam rod stuff. So that's why I wanted to spend some time giving you this context, because it's more or less elementary. So the proof is like this. Let me see. Okay, the proof. So first a definition, which is important, right? A spin 7 structure is the, well, we know that this thing is an associated bundle. And so it's classified by a map from W to the classifying space of the structure group of this bundle, which is spin 8, of course. And this is just classified by the homotopic class of map, which I call S plus. And I know that there is this homomorphism between spin 7 and spin 8. So I can take the induced map, which I'll call BI plus. And so a spin structure without the geometric spin structure, a lifting along this covering. Well, this is not a covering, but along this projection. So a spin structure is just lifting, making this diagram commutative up to homotopy. I don't really need real commutativity, just commutativity up to homotopy. So now what I should do is study classical obstruction theory of this vibration, right? So the first point in the proof is to show that what is called the homotopy fiber of this map, you have to compute this space. And turns out that this space, that there's a very general theorem to do this, is going to be homotopy equivalent to spin 8 modulo spin 7. And this turns out to be homotopy equivalent to a 7 sphere. So let me just erase here. So this map is a vibration with fiber S7. And from this, we can see what are the obstructions to this problem. And the obstructions live in this space, W with coefficients in pi7 of S7, which of course is just the cohomology with integer coefficients. And of course, we know that the obstruction is precisely the Euler class, right? This is a cohomology class of dimension 8. And it's the obstruction lives here. And I am assuming such obstruction vanishes. So there is some map. And obstruction theory is actually good enough to not only give you obstruction, but to compare different liftings. There is a technique to do that, which is the thing that I'm going to review now. And let me see the time, because Okay, I started 12 past 10, right? Okay. So now there is this notion of primary difference. Which, if you have two such maps, say S0, one who maps lifting the spinor bundle, then obstruction theory gives you a way to compare these two maps, one skeleton at a time. So since S7 is 6 connected, the first obstruction and the comparison, what it says is that, let me just say like this. There is a cohomology class that you can compute out of these two maps that lives in the 7-dimensional cohomology of my manifold with coefficients in the 7-dimensional homotopy group of the sphere, which is the fiber. And this is, of course, the integers. And so if these two maps are homotopic, these two maps are homotopic over the 7 skeleton of this manifold, if and only if this difference vanishes. So my assumptions allow me to do that, because H7 is Poincaré dual to H1, right? And this is just the Abelianization. I'm not sure if that word exists, but by Hurewicz theorem, this H1 is just the pi 1 over the commutator, and this vanishes by hypothesis, right? So the primary obstruction vanishes by hypothesis, and then you have to pass to you have to look at the secondary obstruction, the secondary difference. And you cannot, and this process is kind of like a bootstrap process. You're not entitled to go to the next level if you're not done with the previous stage. And this is why I'm doing. I'm giving conditions to make sure that this difference vanishes by brute force, obviously, and then I can continue to the secondary difference. And now this secondary difference compares these two maps, one dimension higher, which is dimension. And now the group that I should put here is not the integers, it's the 8-dimensional homotopy group of S7. And as we all know, or at least we should, is that the joke, right? So this group is isomorphic to the integers modulo 2. Set 2 here. And of course, now I cannot, I can do anything, but this affine function, well, this difference function is enough to the existence and the properties satisfied by this function are enough to this conclusion. So let me just say what the properties I'm talking about, and then you'll see. Okay, so this function, well, you can see this secondary difference as a function from the set of gamma, which is the set of spin structures according to the notation of my theorem. It takes pairs of spin 7 structures, and it returns elements in my group H, which is just this H8W with set 2 coefficients, which of course this is just set mod 2, right? So this is not just a random function, it satisfies three properties. The first property is a cocycle condition, which says that for every x, y, and z in this set gamma, you have like a cocycle condition dxy plus dy z. This is the first condition. The second condition, let me check, is that, well, of course, this the difference between two structures vanishes if and only if the structures are the same. And in this context, it means that these two maps are homotopic. So, and the third property it satisfies is that for every, let me just see here because, okay, for every x in gamma and h in h, there is y in gamma such that the difference between x and y is precisely h. So this property is only telling you that all the possible elements of h are realized as differences of spin 7 structures. So that's why you cannot do better. I mean, and this function d, these properties are satisfied not only, I mean, these differences, all these differences satisfy these properties, not only the secondary difference. So this third point is precisely the reason why you cannot do better. You cannot kind of like take out. And this is actually the proof, because as you can check, and it's a elementary and very fun exercise, you can check that these three properties uniquely characterize a free and transitive structure, a free and transitive action of this group in the set gamma. It's like an adjoint of the action function. So, okay, so that's the proof. Let me see how much time do I have, because I want to make some comments. Okay, I have like 0 minutes. I have to 5 minutes. Okay, great. So further questions, because this is only the beginning of this. I mean, there is a. I mean, this story is just like the first chapter of a much more interesting novel. Actually, the object that geometers are concerned and are more interested is the so-called moduli space of torsion-free G2 structure and spin 7 structures, which is defined as the set of. Do you remember that we had like a self-dual 4-form associated to this spin 7 story? So you can consider the set of all 4 forms that are given by the formula that it was written somewhere. And then in order to have holonomy contained inside a spin 7, you should impose that your 4 form should be closed. So you can consider the space of all positive non-degenerate 4 forms that are closed, and you can mod out by several diffeomorphism groups. But for instance, you can mod out by the connected component of the identity of the diffeomorphism group. And this is the so-called moduli space of torsion-free G2 spin 7 structures. And then it is a theorem by Joyce again in 96 that this is this moduli space is smooth and of dimension a hat of W plus B1 of W. I'm not sure about the B1, but okay, let me stick to my notes. B4 minus of W. I mean, it's a smooth manifold of some finite dimension depending on the topology of the underlying manifold. But apart from this, it is an open question to say something about the topology of this moduli space, right? So today, what I told you can be phrased into saying that the moduli space of, let's say, spin 7, which is just the set of sections of the unit positive spinor bundle modulo the spin diffeomorphisms. I will define it in a second, that this space has two components. This space without modding out, this space, the space of sections, corresponds to the spin structures up to homotopy. Homotopy classes of sections of this bundle corresponds precisely with spin 7 structures in that sense. And what I just told you can be rephrased by saying that this space has two components. And then if I mod out by the corresponding diffeomorphism group, then you can see that this space has at most two components, because, well, you can just the set upstairs has two components, and if I put here like connected components, or in other words, if I compute pi 0 of this space, then I can put pi 0 upstairs, pi 0 downstairs, and this group that I'm not going to define, but the spin diffeomorphism group of W, this is a huge group, but when I take its connected components, this becomes like a discrete group, and this discrete group is acting on a set of exactly two elements, so this thing has at most two components. So, but this is just the topological story. This is so there is a way to more or less do the same, but for this space, and this is done by using the theory of defect invariance. It is an old theory from probably going back to Milner, and it's in its 57 paper of these things, exotic spheres. Yeah, he uses a defect invariant to distinguish those spheres, and there is a theory developed, and it's called defect invariance, and there is a program that has been carried out by Crowley, Gutt, and Nordstrom in 2015. This is still in a preprint form, but they were able to kind of like compute the defect invariance corresponding to a similar story, but in the G2 context. And they were able to prove that the corresponding moduli space of torsion-free G2 structures can have more than one connected component. And they use this idea of defect invariance and eta invariance and stuff. And I believe that something similar can be done for the spin 7 context, for the spin 7 group. And right now I'm working on extending that theory to this group, but I don't have any results to share with you. So that's it. That's what I wanted to talk.
So, any questions here or in the internet room?
So hi Raúl, so thanks for the nice talk. So my question is the following. I know you were in my talk, and we were talking about these Clifford structure, even Clifford structures. So actually, I didn't remember when you asked me about the topology questions, but we do have some diagrams like yours.
Yeah.
Meaning, so we have a paper where we study not spin 7 structures, but we know the structure groups. So it's like a spin R times some centralizers.
Okay.
And we really know when these leads to spin structure.
Right.
So I think so probably I mean this is was somehow fundamental in your proof, right?
Yeah.
So I think it would be nice if we can talk and think
sure,
about.
Sure.
I mean, it's not. It probably there is a lot of work. Maybe you're interested. I think it's quite interesting, but because the group here is not anymore spin 7.
Yeah.
You can have a spin R times SO something,
okay.
or U something, or SP something, right? But we really know when does this lead to a spin structure.
Oh.
So I mean, do you think?
Yeah, for sure. Yes. I mean, as long as you have like, as long as you can construct a vibration like this, and my impression is that you have like your bundles have precisely that property that you can compute these fibers. Then yes, of course, it's more or less standard, not easy, but standard way to compute the instructions and do this construction. So yeah.
Thank you.
Reasonably doable, I guess.
There's a question here from the internet audience, which is the following. Which could be the implications of spin 7 structures in theoretical physics?
Oh, man. Well, I'm not the right person to give a answer to that question, but these things appear in string theory as far as I know. So who knows? I mean, I'm not the right person to say anything more than these things appear in string theory in one of its forms. That's it. I can give reference to people that probably can. You should ask Hugo Garcia Compean, which is in Simbestav. He will probably know, or I don't know, but I'm not the right person to answer that. Sorry.
Thank you.
Yes.
So if you have this spin structure, you get a Ricci-flat metric, right?
A Ricci-flat, yes.
But you can have more Ricci-flat metrics, or I mean, somehow you can study this model space of Ricci-flat metrics.
Yes, I mean, in principle, yes. I mean, you can run this machinery like backwards. You since spin 7 is contained in SO8, well, via this spin 7 representation, then you will have like abstractly, you will have a metric and an orientation. And the thing is like, as far as I know, I'm not sure if this map that to this form associates a Riemannian metric. I'm not sure if this map is surjective, but I mean, in principle, as I see it, it is possible to have Riemannian metrics. Yeah, the problem is that you really don't, well, you have all the you need to, given a Riemannian metric, you can answer whether or not this abstract Riemannian metric has holonomy in spin 7. You should use this thing called the intrinsic torsion of your structure. But I don't know if all the metrics are of this form. I don't know. But yeah, in principle, it is possible to answer this type of question for an abstract metric coming just from this embedding.
Any other question? Well,
I'm just wondering. I mean, once you have that the structure lift to spinate, then you can consider the triality in spinate, right?
Yeah.
Does this give you another type of spin structures?
No,
spin
actually,
structure?
I was confused at the beginning because I thought that this theorem predicts that. Sorry. Well, maybe later. But this theorem actually, a nice corollary of this theorem that I completely ignored, but that was a mistake, is that a spin 7 manifold, meaning a manifold with a spin 7 metric, has at most has exactly two spin 7 structures, right? Because by Joyce's theorem, such a manifold is simply connected, and of course, the trivial group is abelian, so so this theorem applies. And at the beginning, I was confused about that fact. I thought that the other spin structure had to do with triality or stuff, but no. I mean, it's much more simple. If you see the formula I've written for the 4 form, you'll see that it's quadratic on the spinor, right? It's a polynomial in your vector fields. So if you have a spin structure, say pi, you can construct your spin 7 metric. And then if you plug in here minus the spinor, since this is quadratic, this minus cancel out, and you get the same metric. So the content of this theorem, the content of the corollary that I just mentioned, is that these are the only two, well, morally, I guess, this is these are the only two possibilities for that metric. These are the two. Now, but yeah, triality doesn't enter in this picture. I'm fixing. Yeah, you can say that triality is the existence of 3 different spin 7 subgroups inside here. This one, the one that corresponds to negative spinors, and the stabilizer of a vector in the vector representation. These are the 3 spin 7 subgroups, and here I am fixing kind of like the subgroups. So I don't know if that answers your question, but that's.
Yeah, so I suppose that somehow they are isomorphic in some sense. But yeah, it answered my question. Thank you.
Well, I think isn't any other question? Well, let's thank again to Raúl